Remember, no matter what context we're in, welcome in, Derek. Welcome in, Adam. No matter what context we're in, differentiability means local linearity. Whether that be a tangent line in 2-space or the tangent line on a curve for vector valued functions, or a tangent plane in 3-space, differentiability means local linearity. So one of the ways that we looked at local linearity back in the Calc 1 is the concept of a differential. Differentials kind of get back to the historical usage of derivatives that Newton used when he was formulating physics. Here's the idea. So this is back from Calc 1. So if f was differentiable at a point x equals a, that meant that f of x was roughly equal to f of a plus f prime at a times x minus a. And if we recast x, if we just, as being, or call delta x be x minus a, so x is a plus delta x, then we could say that f of a plus delta x is approximately equal to f of a plus f prime of a delta x. So the idea is we're changing a by some amount delta x. If f is differentiable, then I can approximate this new function value, delta x units away, by starting with f of a itself and then tacking on this sort of linear correction factor, f prime of a times delta x. So this delta x, since x was the independent variable, this was called the increment in the variable x. We made this synonymous with the differential. So delta x in this particular context was called the same as dx. But then the quantity f prime of a delta x, this was defined to be the differential. So we could write this as f prime of a dx. This was called the differential in y, thinking of y as the dependent variable f of x. And so what we could think of here is, if I look at f of a plus delta x minus f of a, so if I subtract the f of a off here, that would be roughly f prime of a delta x. What I can think of this as being, this is our actual change in f of x. This is the actual change in y on the curve, y equals f of x. This is going to be approximated by, what is this? Well, f prime of x is the slope of the tangent line. Delta x is the change in x. So this is going to give me the change in y on the tangent line. So this is the dy, which is the change in y on the tangent line. And so putting all this together, f of a plus delta x can be recast as the following. You start at f of a, that's your known value, and then you tack on the dy, which is the approximate change. Okay, that's an estimate of the change. So does all this ring a bell? This is all what's going on algebraically. We can look at the graph here in a minute. But you remember this kind of thing? So if I'm looking at the graph here, right? So this is our This is our delta x. And since x is the independent variable, we're just going to call that dx. We're going to associate or just call those things the same in this context. The actual change in the function values, that's the actual change in the function. That's the change in y on the curve. And then this is your differential, f prime of x dx. That's your change on the tangent line. And as your delta x goes to 0, we can see that the change here gets smaller and smaller. And so it does a better and better job of approximating. So this is what this was all about from Calc 1. All right, so this should all look familiar. Yes or no? Remember this kind of thing? Well, here we go again. Functions of two variables. Now we have two independent variables, x and y. So we're going to let dx be delta x and dy be delta y. All right, so once again, those are the increments of the independent variables. And we're going to define dz as follows. So if I look at how dy was defined, dy was defined to be f prime of x dx. This is the rate of change of y with respect to x times the change in x. So symbolically, it looks as if we're just canceling out the dx's. Here we've got two independent variables, dx and dy, so dz would be the approximate change in z. We're going to set that equal to the rate of change of z with respect to x times the change in x. So this is going to calculate the change in z in coming from the x direction. And then I've got my fy delta y. This is your change in z coming from the y direction. And so the same thing's going to happen. The dz approximates the change in z on the tangent plane. So if I'm looking at f of x plus delta x, y plus delta y, I can approximate that by f of xy plus dz. It works the exact same way it did before. All right, so here's sort of the graph for that in 2 dimensions. That's what we're doing. All right, so for example 4, we're given a function f of xy equals x e to the 2y. Does this look familiar? This is the exact same one we had yesterday. Find an expression for the total differential dz at the point 1, 0.5. So dz, once again, is looking for the approximate change in z as a result of changing x and y. So we look at the rate of change of z with respect to x at the point 1, 0.5. Times our dx plus fy at 1, 0.5 dy. And these are values that we looked at yesterday. So we got these yesterday. We took derivatives, we showed they were continuous, we proved f was differentiable, and then we plugged these values in. We got 2 for the fx, and we got a negative 2 for the fy. So that's our dz. Find f of 1, 0.5 and use differentials to approximate 0.9, 0.55. Does your answer look familiar? Okay, so we look at f at 1 comma 0.5. We go back to our original function and plug in the x and the y. We get 1 from that. Use differentials to approximate f of 0.9 comma 0.55. So we want to use the approximation here, f of x plus delta x, y plus delta y, is approximately equal to f of xy plus dz. So the xy that we know about is 1 comma 0.5. Oops. So let's figure out what this is going to be here. They want us to approximate f of 0.9, 0.55. Using f of 1 comma 0.5. So we got to figure out what the delta x and delta y is. So their x here is 1 and the y is 0.5. So 1 plus delta x is 0.9. So delta x is 0.9 minus 1. It's the new x value minus the x value we know about, negative 0.10. Y plus delta y is 0.55. So 0.5 plus delta y is 0.55. So delta y is the new y value minus the y value we know about. So I can calculate now the dz. The dz was 2 dx minus 2 dy. Since the x and y are independent variables, the delta x's and dx's are the same. So 2 is the rate of change of z in the x direction. So that would be 2 units of z per 1 unit of x. I'm changing by negative 0.1 units of x. Minus 2 times dy. So that minus 2 is the change in z with respect to y, and I'm multiplying it now by the change of y. So I go through the arithmetic here. What do I get? I got a negative 0.2 minus a 0.1. So a negative 0.3. And so this represents the approximate change in the function values, the approximate change in the z values. So before we go to the next slide here, any questions on figuring out the delta x, the delta y? Those are the dx and dy, or the dz. Do you see where all the pieces parts are coming from here? So f at 0.9, 0.55 is approximately equal to f of 1, 0.5 plus dz. F of 1, 0.5 is 1. dz is negative 0.3. And that's 0.7. Okay. Now, does that look familiar? Well, when we went and did the tangent line, or tangent plane rather, yesterday, to get the linearization, that's the exact same value we got at the linearization. You follow? And hopefully that makes sense. All right? Because if I go through and look at my formula for the linearization that I had yesterday, what was that? That was f at 1 comma 0.5 plus fx at 1 comma 0.5, x minus 1 plus fy at 1 comma 0.5, y minus 0.5. And so if I plug in 0.9, 0.55, look at what I get. (0.9 minus 1), the new x minus the old x, that's exactly the delta x. 0.55 minus 0.5, the new y minus the old y, that's exactly delta y. So this is your delta x, this is your delta y. This piece right here is exactly the same as the dz. You follow? So one of the big things back in Calc 1 I would ask students to pontificate about is how using differentials is just another way to use the linearization. Same thing here. Okay? We're just lumping this entire piece. That's your dz. We're starting at the known value. We're looking at how things could change. We're doing a first order error correction in the x and the y directions. Okay. Do you see how all this fits together? All right, so we're just rebranding, okay? All right, let's take a look at error analysis. This is if you had me for Calc 1, there's a couple people in here who had me for Calc 1. If you had me for Calc 1, this is the exact same example we do in Calc 1. Back when I was taking physics, and Rick may or may not be able to confirm this, this is how we did error analysis in physics, is we used differentials. Even though we barely knew what derivatives were, we used differentials. This is not how they do error analysis now. They use a statistical method, and I've talked to Dr. Thomas and Professor Ciferno about these things. And I got a nice paper. Dr. Thomas dug up one of his textbooks and talked about how these things get done. It's interesting to compare and contrast these methods, though, because they do give very similar errors. So here's a scenario. Here's where you can think about differentials out in the wild. We got the density of a substance rho. So this looks like P, but it's actually a stylized P. This is actually rho, and we'll see rho again later on. It's calculated by dividing the mass divided by the volume. So rho is m over v. Hopefully that's something you've all encountered at some point. A scientist collects 5 plus or minus 0.5 mils of a substance and determines its mass to be 68.2 plus or minus 0.1 grams. So that's fairly heavy. She computes the density by using the 68.2 grams divided by the 5 mil to get 13.64 grams per milliliter. But in doing that calculation, you've got these uncertainties that are feeding into it, right? And so what we can do is use differentials to help us approximate the error incurred by using these measurements. These errors are because we're observing things, we're measuring things, all right? Any measurement you collect will always have an uncertainty associated with it. So first off, we're asked to find the total differential d rho in terms of dm and dv. So we have rho is equal to m over v. And so d rho would be the partial derivative of rho with respect to m times dm plus the partial derivative of rho with respect to v dv. So this is how it would look like using Leibniz notation. Now if I look at what's going on here with these variables, I could rewrite this as m times v to the minus 1 power. You take the partial derivative of rho with respect to m, you're treating v as a constant. So what do you get when you take the partial derivative of rho with respect to m? So what's the partial derivative of rho with respect to m, treating v as a constant? Yep, 1 v to the minus 1 power. Good. It'll just be a v to the minus 1 dm plus, now I need the partial derivative of rho with respect to v, treating m as a constant. See, m would go along for the ride. What's the derivative of v to the minus 1 power? It'd be minus 1 v to the minus 2, because we subtract 1 from the power. So minus 1 is minus 2 dv. Yep. So now, and if you rewrite things in terms of fractions, that's what you get. All right. So what we can do now is plug in the values for v and m, and we can use the plus or minus here as the values for dm and dv. So we can look at the dv is plus or minus half a milliliter, and we can look at the dm to be plus or minus 1 gram. And we can feed all of that into our formula for d rho. So d rho would be 1 over v dm minus 1 over v squared, m rather, over v squared dv. V rather was 5 plus or minus 5. So put in 5 milliliters there. The dm was plus or minus 0.1 gram minus the 68.2 grams divided by the 5 milliliter squared times the plus or minus 0.5 milliliter. And I always do this, like even back in Calc 1, I always like to carry units through to make sure that they end up making sense. So here I would have plus or minus 0.1 over 5 grams per milliliter, so that's a unit of density, that's good. Minus, I'd have 68.2 over 25 times plus or minus 0.5. And if I look at the units here, I'd have grams per milliliter squared times milliliters. So one of those milliliter factors would cancel out, and I'd have grams per milliliter. So I'm getting units of density, which is good, right? Now the question becomes, how do I make a conservative estimate here? So I like to think of like worst case scenario. So the worst case scenario is these errors add up. So I guess the worst case scenario is we would have a plus here and a minus here so that these errors would combine. And if you go through and do that arithmetic, which I'm not going to take the time to do here, let's see what we get. We'll trust what I got on the handout here. Plus or minus 1.384. And this should be grams per milliliter. I'm going to have to remember to go back and plug that in because you want to have the units on there. 1.384 grams per milliliter. So that would be what's called the approximate propagated error. It's the error that when using those two measurements in that manner, with those uncertainties with the measurements, this is a guesstimate of the error. And then the question is, okay, well, is that a big or small number? So that's why we do the percent relative error. So d rho, once again, this is the approximate propagated error. So if I take d rho divided by rho, that's plus or minus 1.384 grams per milliliter, divided by the calculated amount, 13.64 gram per milliliter. Once again, you can see the units will cancel out, and I'll be just left with a number, a relative number that I can interpret as a percentage, and this is roughly what, like 10%? Yeah, it's roughly 10%. So it's 0 plus or minus 10, which is roughly plus or minus 10%. Okay, which is probably completely unacceptable, right? I don't know in the lab. I know they banter about the 5% rule. It just depends what you're doing. Okay. So once again, I think nowadays they do the error differently. They just sum up the squares or something, and they have rules for it that kind of come out of nowhere. But that's one application of differentials. All right, extensions to more variables. We talked about 1 and 2 yesterday. What about the total differential dw? So if we have w as a function of x, y, and z, how would you generalize the notion of dw? So once again, in one dimensions, if y is equal to f of x, dy was f prime of x dx. Z is a function of x and y. dz is fx at x, y dx plus fy x, y dy. So if w is a function of x, y, and z, what's been the mantra for a lot of what we've done here? When you're going from 2 to 3 dimensions, all you're going to do is tack on a what? Tack on a z. So you're going to have your rate of change of f with respect to x times your change in x plus your rate of change of y with respect to y plus your rate of change of z with respect to z. Once again, if you have a differentiable function, then that means the function is locally linear. That means you can approximate the change in the dependent variable by looking at the slopes in the individual directions and multiplying those slopes by the change in the independent variables. So hopefully you're seeing this this notion here. To calculate the volume of a box, a student measures its dimensions with a ruler, which is accurate to within 1/8 of an inch. They find the length is 5 inches, the width is 4 inches, and the height is 2 inches. Use differentials to estimate the percent relative error in calculating the volume of the box to be 40 cubic inches. All right, so here's another application. What are we calculating here? A volume. And how are we getting that volume? We're measuring the length, the width, and the height. So what's an equation that relates volume with length, width, and height? If I call volume equal to V, then what's volume equal to? Length times width times height. Good. So LWH. I'm trying to I measured L is 5 inches, W is 4 inches, H is 2 inches. But all of these have an uncertainty, and the uncertainty of all of them is the same because we use the same ruler to accurate within an eighth of an inch. This is all plus or minus 1/8. Right? So once again, that plus or minus, those are the differentials. So if I want the percent relative error, I'm going to use the differential here to approximate the propagated error, and then divide it by the 40 that I got. So to get to the dV, I take the partial derivative of v with respect to L, dL, plus the partial derivative of v with respect to W, dW, and the partial derivative of v with respect to H, dH. So there's my differential expansion there. And there's a nice symmetry between L, W, and H. What's the partial derivative of v with respect to L? So partial derivative of v with respect to L means we're treating W and H constant. So what do we get for that? Yep, WH. So WH dL plus the partial of v with respect to W. LH dW, and then partial of v with respect to H. There you go. Very good. Thank you, Derek. Right, nice little symmetry. Now we just plug in the values. We plug in the L, W, and H. We plug in the plus or minus 1/8. So we'll go to the next slide and do that. So the dV. Once again, this is estimating the approximate propagated error. I get W times H. W times H would be 20 times plus or minus 1/8. WH are both measured in inches. This is measured in inches, so this would be in inches cubed. Plus LH, that would be 10 times dW, which once again is plus or minus 1/8. Each of these are measured in inches. That's measured in inches, so this is inches cubed. Plus LW. Oh wait, did I mess this up? WH should be 8, not 20. Yeah, this should be 8. There you go. This one is going to be 20 times plus or minus 1/8. Once again, inches cubed. So we've got what? 18, 38. So I got plus or minus 1/8, 38 inches cubed. Let's see here. What's 38 divided by 8? That's what, 19 fourths? And what's 19 fourths going to be? That's going to be almost, that's a quarter shy of 20 fourths, right? That'd be plus or minus 4.5, or 4.75 rather, cubic inches. Is that right? Did I do my arithmetic right here? On a summery morning in October. Is that good? So then my dV over V would be plus or minus 4.75 cubic inches divided by the measured calculated volume with those. It should be plus or minus. Let's see, what do we get here? 11.9%. So once again, we're just hitting big numbers and errors, but there you go. Okay. So in addition to the actual calculation, right, please take some time to look at what the differential was in Calc 1 with a single variable and how it just generalizes and why it generalizes the way it does. We're adding on another independent variable, so then we're adding on the change by taking the rate of change in the variable times the change in the variable. So that's local linearity in each of those dimensions. All right, to cap everything off here, I do want to work through a proof by definition, because we worked yesterday to create this definition of differentiable to mean locally linear. So it's worth taking the last few minutes here and walking through how would you actually prove a function is differentiable using the definition. So this was this is how we can recast the definition here. Once again, if we look at defining delta x to be x minus a, so x would be a plus delta x. So this says that if we're starting at f of ab, so if we're starting at the point ab and we move delta x units away from a and delta y units away from b, to be locally linear means we can look at the change coming from the x direction, the change coming from the y direction, and then we'll have these two error functions left over, both of which go to 0 as delta x and delta y go to 0. So what I find is helpful to do is to evaluate, right, take the function itself and subtract off this part. Remember this part, right, that's your tangent plane equation, more or less. So you're taking the the z value at the surface, right? So f of a plus delta x, b plus delta y. This is the z value on the surface, z equals f of x, y. The f of ab plus fx at ab delta x plus fy at ab delta y. This is the z value on the tangent plane, and we're going to look at the difference of these, and we're going to show the difference of these can be written in this specific form. Right? So first we compute all the ingredients. So here we're looking at f at a plus delta x. Everywhere we see an x, we're going to replace it with the quantity a plus delta x. Everywhere we see a y, we're going to replace it with the quantity b plus delta y. So here's our x times our y squared. And so we FOIL things out, aka distributive property, everything out. This is what we get when we multiply all that out. Okay? And once again, I encourage you to work through the details here in the privacy of your own home. Next, we find the partials fx and fy, just like you do normally. And then we plug in the numbers a, b to fx and fy, and then we create this expression, which once again is going to represent the z value on the tangent plane, and we get this. All right. So now we kind of compare what's the same. Right. This is the actual retail value on the surface. This is the value on the tangent plane, and we can go through and see what's the same. I've got an ab squared in both, so those are accounted for. B squared delta x, that's in both, so that's accounted for. And the 2ab delta y, that's in both, that's accounted for. And so I look at the leftovers. So this, folks, this represents, this is the error that we've got. Right? That's the error we get if we approximate the actual retail value of the function by the function on the tangent plane. So what I need to do is get the error to look like what I've got up here. So I need to take some of it, write it as an epsilon 1 delta x and an epsilon 2 delta y, where the individual epsilons go to 0 as delta x and delta y go to 0. So it turns out there's a couple different ways you can do that. So I could take what we have here. So once again, that's our leftovers. I could factor a delta x out of these two things, and I could call that an epsilon 1, and notice epsilon 1 goes to 0 as delta x and delta y goes to 0, and then I could just take the delta y out of this one and call that my epsilon 2. And both of these go to 0 as delta x and delta y go to 0. But you can, and this will happen often, you can group these things other ways as well. For example, you could just look at this one and write this as 2b delta y delta x. Call that epsilon 1. Factor delta x, in other words, out of this term. And then factor a delta y out of these last two. You can call this epsilon 2. These also satisfy the condition that epsilon 1 and epsilon 2 go to 0 as delta x and delta y both go to 0. And so that'll happen in general. There'll be multiple ways to regroup this error, but as long as you can find a way to regroup the errors in this way, then you've shown that the function is locally linear, the function is differentiable. Okay. So on this week's take-home and test, we don't get into one of these. I think I'm gonna give you one next week, because you've got enough going on with everything else in this section. Okay. So speaking of what's going on next week, let's take a look at your next take-home and look at what you can start working on now with what we've covered. Now, tomorrow and Friday, we're going to be talking about the chain rule. So we're going to go back and get back on in sequence with the book on that. The key to all of that, though, the chain rule, why it works, it all comes from local linearity.